Hello, my name is Winston Sanders. Now, unfortunately, for some reason, my window has to kind of be towards the center of the screen. Otherwise, it won't transfer to other slides. I don't know why that's why I like that, but I've been having to do this for the past couple of hours trying to make it work. But this is the best I can do. I know it'll obstruct some of what I'm trying to say, so I'll try to be as descriptive as I can. But unfortunately, I cannot do anything else without it breaking my computer. Regardless, I'll be going over Mercury 2 Fulminate and Mercury 2 Cyanate. My name is Winston Sanders. My teammates are Louis Banda and Chris Corraine. Unfortunately, we did have a fourth by the name of Vitaly Hotch. However, she has recently dropped out of Chemistry 2, and as such, she will not be part of this presentation. Now, Mercury 2 Fulminate and Mercury 2 Cyanate are very similar in terms of their structure, and due to cyanate being relatively difficult to handle, there's not much reliable information on it that we can get without having to pay very, very expensive money that I'm sorry we can't really do as a moment. So instead, we have decided to actually look more into their polyatomic anions, as they are interesting in the fact that they have the same atoms, but on typical sort of going through them, they actually have different structures. And a great example of this would be their Lewis structures. So for the fulminate anion, which has atoms of carbon, nitrogen, and oxygen, we can see they have a triple carbon-nitrogen bond, or three singular bonds, but we usually say triple bond, and a single nitrogen-oxygen bond. Carbon has a single lone electron with a -1 charge. Nitrogen has again a lone electron but a positive +1 charge. And oxygen has two lone pairs, a single lone electron, and a -1 charge. Meanwhile, the cyanate anion has the exact same atoms carbon, nitrogen, and oxygen. However, while they still have a triple bond for carbon and nitrogen, they actually have a different sort of single bond for carbon and oxygen instead of nitrogen and oxygen, even though they're the same atoms. Nitrogen has a lone pair, and oxygen has two lone pairs, a single lone electron, and a +1 charge. Even though they are the same exact atoms, they have different charges for their respective atoms. And we can see this further when we look into their resonance structures. In order to find the resonance structure, usually find first their formal charge, which in order to find the formal charge, you need to go through their valence electrons and subtract it from the bonds and dots per atom. And in this case, even though they all look somewhat similar, you could actually see that the second resonance structure would be the most stable, as oxygen in this case has a -1 charge. Now, when it comes to deciding resonance structures, especially when some of the resonance structures might actually be somewhat similar, you're best to actually find whatever has a minus charge on their most electronegative atom, which in our case is oxygen. When you compare their oxygens, the resonance structure, their formal charge for oxygen for the first resonance structure is 0. For the second one, it's -1. And for the third one, it is a +1 charge. And since we want to put our minus charge, the most electronegative, it would be the second resonance structure here that would actually be the most structurally stable. Now, for cyanate, it would be a little bit different, as they both actually have a -1 only on different atoms. However, if we go back to our electronegativity sort of understanding, it would still be a -1 charge that we would want on our most electronegative, which would still be oxygen. So you would actually still choose, in this case, our second resonance structure for oxygen in order to be the most stable for cyanate. This is kind of unique in the fact that even though, again, cyanate and fulminate actually have the exact same atoms, you can see is oxygen, carbon, and nitrogen, but for some reason they have slightly different resonance structures, which ends up kind of showing off of why they're different. This is mostly due to the fact that for fulminate, nitrogen is in the center of the linear sort of structure, but carbon is actually in the center for cyanate, which makes it have a slightly different. And this slight difference can be the difference between fulminate, which is relatively more easier to handle, compared to cyanate, which is very much less easy and thus much information. Regardless, This is Winston Sanders. Thanks for watching.
Okay, my name is Chris. Today I'm also going to be talking about the differences between mercury 2 fulminate and mercury 2 cyanate. So the anion structure for mercury fulminate is CNO. The mercury has an incomplete octet and the compound is highly unstable. Whereas in mercury 2 cyanate, the anion structure is OCN. So there's oxygen, carbon, and nitrogen. Mercury has an incomplete octet and the compound is stable. Another set of differences is that for mercury to fulminate, the molecular geometry is linear, the bond polarity is very high, net dipole moment is large, and the stability of the compound is very low, like I mentioned before. But for mercury to cyanate, the molecular geometry is linear, the bond polarity is moderate, it's not very high, and the net dipole moment is small, the compound is highly stable. And So these are the resonance structures and their impact on reactivity. So for mercury 2 fulminate, the carbon carries substantial negative charge. Nitrogen is often positively charged. Oxygen is negatively charged, and charges are not evenly delocalized. Okay, so there's a high internal charge separation, which means high potential energy, and the thermodynamic stability. So the resonance stability is pretty poor. Charge distribution is highly uneven, and the overall energy is high. Bond strength is like the weaker mercury and carbon bond. The electric negativity match is poor, and activation energy is so. What pretty much everything means is that mercury to fulminate is an unstable molecule.
Hi, this is Luis Banda. I am doing the rest of this. Nope. Okay. Hi, this is Luis Banda. Here we have the resonance structures and their impact on reactivity for mercury 2 cyanate, the anion. There are two main resonance structures for this anion. First, we have the triple bond on nitrogen to carbon, and the second is a double bond on oxygen and nitrogen on the carbon. So the most stable version of these two resonance structures is the first one which has the oxygen having a -1 charge and the rest having 0. Oxygen usually likes to have a -1 charge and um, basically share its electron. So that's why the first one is the most stable of all the other resonance structures. So it has less reactivity. Using the thermodynamic stability, resonance stability is strong, charge distribution is well delocalized, and that negative oxygen, and the overall energy is low because it's stable. And kinetic stability, the bond strength between um, the mercury and the oxygen where it's connected to is strong, the electronegativity match is good, and activation energy is high, which means that it needs a lot of energy in order for it to react to things. That's why mercury 2 cyanate is a stable molecule. So, for chemical and physical properties, mercury 2 fulminate is a crystalline solid and is white in color. Mercury 2 cyanate is a solid and white in color as well. Chemical properties for fulminate. Fulminate is toxic, flammable, and highly reactive, while cyanate is toxic and somewhat reactive. Since mercury to fulminate is a very reactive chemical or molecule, we don't really have many physical properties that we can get from it since it reacts really well um, in room temperature. Friction or slight heat cause it to react, so we can get a lot of uh, physical properties from it. On the other hand, mercury cyanate is a very rare chemical to see, so we don't have a lot of physical or chemical properties for it as well. It's mostly seen in labs and stuff like that. But yeah, that's for that. Relevance in our world: Mercury 2 fulminate was widely used as an explosive initiator. It was the primary explosive to start the explosion in blasting caps. Since it's highly reactive, it is best to use something that's highly reactive to get your reaction for your explosion going. That's why it was good. It has since been replaced since it's toxic and it is somewhat expensive. Mercury cyanate, we don't really see it often since it is a rare molecule, but it is like a byproduct for cleaning water since it's used when it's not used. It's since it's made when you're detoxifying water and adding cyanide into the water. It the cyanide um, just gets pushed out, and that's it. Thank you.